Hello students and welcome back for our second lecture on radical reactions. So last time we talked about the sixth type of fishhook arrow pushing patterns that would represent the steps in radical mechanisms. We talked about the types of steps in radical mechanisms, including initiation, propagation, and termination. Finally, we talked about how radical chain mechanisms are used to halogenate hydrocarbons. And now we're going to talk about the regiochemical and stereochemical considerations involved with halogenation reactions, radical halogenation reactions. So when we take a look here, if we have, for example, in propane, we've got two types of hydrogen atoms. We have those attached to the secondary carbon and those attached to the carbons on the end here, of which there are six. So when we have this halogenation with chlorine, as we discussed last time, the first step in the halogenation, the hydrogen abstraction, is spontaneous for chlorine, and so it will occur very readily before the second step happens to produce the final chlorinated product. However, for bromination, the first step is quite slow and involves a first step that is not spontaneous. And so what we're going to see is that this is going to result in a much more selective bromination, where we can decide where the bromine is going to go in a particular spot. So for the chlorine atoms, there's no difference between these two. Essentially, both will proceed spontaneously and quite quickly as well. So they'll be thermodynamically favored because, as you can see here, going back to the energy diagram, because they have a lower energy for the products and the reactants. However, the first step will be much faster for the chlorination to produce the radical after the hydrogen abstraction. So the result is that a secondary radical will be produced just as readily as a tertiary, or as a primary, even though the primary is less stable radical. All of these are going to happen quite quickly, and so in the end, you're going to get chlorination at the primary position just as readily as you would get it from the secondary position. But since the secondary radicals are more stable than the primary, we're going to get a little bit more of the secondary radical. These will be produced a bit more easily. And so we can see here an energy diagram representing both. The primary radical is less stable, it's higher in energy than the secondary radical. And so the result is that we'll more easily, more quickly produce a secondary radical than the primary radical, faster, because of lower activation energy right here for the production of the secondary radical in the first step. This is for the first step of the chlorination, the hydrogen abstraction. With the bromination, it's overall going to go much slower because the first step is going to have a high activation energy, but also it's going to be much more selective because the slow step is going to be very slow, and it's going to produce mostly secondary products because those are lower in energy, and then those will be the ones that go on to produce the products very readily in the second step, whereas the primary radicals are not going to be produced pretty much at all. So the bromination is much more regioselective than the chlorination, and this can be explained by the so-called Hammond postulate. So you may remember from way back when, early in the class, we talked about the Hammond postulate, which says that a transition state will have a structure that is more like the reactant or the intermediate or product that it is closer in energy to. So in the case of the chlorination, the transition state is very much like the reactants because it's closer in energy to the reactants. How in the hydrogen abstraction here, and the intermediate is much more stable as a secondary radical. However, in the case of the bromination here, the intermediate, that's produced, whether it's secondary or primary. It's just, remember, we said that it was exothermic to produce the intermediate here for the hydrogen abstraction. The hydrogen abstraction was exothermic for the chlorination. and endothermic for the bromination. So see the hydrogen abstraction here, exothermic, lowering in delta G for the chlorination, whereas it's endothermic, that first hydrogen abstraction step, for the bromination. So what that means is that the transition state will more closely resemble that of the intermediate. And so that transition state is going to be here, closer to the structure of that intermediate. What does that mean? Well, when we're looking at the transition state, what it means for the chlorination is that the hydrogen bond, the bond between the carbon and the hydrogen will be mostly intact, only beginning to break. And the hydrogen-chlorine bond will just barely be starting to be formed. However, in the case of the bromination here, the hydrogen bond between the carbon and hydrogen will almost be completely broken by the time it reaches the transition state. And the bond between the hydrogen and the bromine will almost be completely formed. And what that means is that the transition state is very, very much like a secondary radical. This is almost a radical, right? As soon as this bond breaks, this becomes a secondary radical. And so what that means is that's going to have a really, really big impact on whether, the stability of the radical, whether it's going to be secondary or primary. A secondary radical will be much more stable, and thus the transition state will be much lower in energy than for a primary. So just going back to the chlorination, you saw that the secondary radical had a lower activation to energy to get there, but barely, right? With the bromine, it's going to be a big difference. The secondary radical transition state will be much lower in energy than the primary. And so this is just basically repeating what I said. For the bromination, the stability of the transition state largely depends on the stability of the resulting radical, secondary being much more stable than primary. For the chlorination, the stability of the transition state does not really depend much on whether it's primary or secondary, because it's hardly a radical once it reaches the transition state. It's just barely starting to break this bond. And so that contributes to the regioselectivity of this change. So here's the overall energy diagram for the first hydrogen abstraction step for chlorine versus bromine. You can see that for a primary radical versus secondary versus tertiary, the activation energy is pretty close to the same. And so it's going to be a little faster to produce the tertiary radical than it is the secondary or the primary, but not by much. They're going to be competitive with one another. However, in the hydrogen bromination process here, the activation energy is going to be significantly greater if for the production of a primary radical versus a secondary versus a tertiary. And so that's what contributes to that regioselectivity in the case of bromination versus chlorination, is that the production of the more stable radical is just going to be significantly faster. And once we get past this slow first step, the rest is really quick. So when it comes to the chlorination here on a potential tertiary versus primary here. So we can get chlorination, which will involve a tertiary radical intermediate, which would involve putting the chlorine here on the middle carbon, or we can have one that involves a primary radical intermediate, which would be putting the chlorine on one of these carbons here. In the end, what we're going to get for the chlorination is about 65% of the tertiary alkyl halide and only 35% of the primary alkyl halide. And that's pretty crazy too, considering that there's only one hydrogen that can be replaced on the tertiary, and there's 9 on these. Each of these have, there's, in terms of hydrogen, there's 1 hydrogen here, but each of these have 3 hydrogens, 3 hydrogens, 3 hydrogens. So in terms of statistics, there's 9 hydrogens to 1 that you could replace. And we can see here that we get 35% chlorine, 65% chlorine. But with the bromination, this is much more pronounced. We get 100% of the tertiary and absolutely 0%. Even though there's 9 times many hydrogens, that primary radical is just going to take too much energy to get to especially to the transition state for it. So that's what slows down that reaction. And so the bromination at the tertiary position happens 1,600 times more faster than at the primary position. So we get almost all addition of bromine to the tertiary position. So fluorination, as we talked about, very spontaneous in both steps, very fast. And so uh, the the regioselectivity, it's not going to be very regioselective at all. It will halogenate almost at the same rate as primary, secondary, and tertiary. Tertiary being having a little bit of an advantage there. When it comes to chlorine, this should say chlorine, not C1, but chlorine, we can see that the primary very, very slow, secondary much faster, tertiary even faster. But the secondary and tertiary are very competitive with one another. You're going to get a significant amount of both. Even if you have primary, you'll get some. And then adding bromine to a primary position, very slow. Secondary, somewhat faster, but tertiary is way, way faster. So the addition of bromine is going to basically only happen at the tertiary position if that is available. It's way, way faster than secondary, which is way, way faster than primary. So if we're halogenating butane, for example, here, now this, when it's halogenated, produces a chiral carbon, right? Right now it's not chiral. Let's say the secondary position, because we have two hydrogens. But if we replace one of those hydrogens with a chlorine, so if we take this and we replace it with a chlorine, let's say, actually, let's say I had wedges and dashes here, right? So this is a wedge, this is a wedge here, and this is a dash. Then let's say we take one of these and replace with a hydrogen or with a chlorine. We have a chiral carbon, right? And so we're going to get a new chiral center here. But remember that this goes through a radical intermediate, and that radical intermediate, although it's like a shallow pyramid, we talked about it before, interconverting. So it behaves more like a carbocation, like a trigonal planar site. And so when we have the addition of the chlorine, it could easily happen from either side. And so the halogenation reaction with 2-chlorobutane will produce a racemic mixture. And so notice that the stereochemistry is not shown here, no wedge or dash. It's because we'll get either one. So you would either show both, or you would say this, and it's a racemic. When it comes to adding the chlorine on the primary position, we know that we'll be competitive with the secondary position because this is chlorination. However, this is not a chiral carbon because there are two hydrogens attached here. So, as I said, recall that when we have a radical intermediate, it behaves as if it's trigonal planar. And that's why when we finally have the coupling with the chlorine, it can happen equally from either side, essentially. And so we get this racemic mixture here. So adding the chlorine in the so if let's say this is a question on a test, and I give you this guy here, and I say, what are you going to get? What are the products? The products will be a chlorination at the secondary position with a racemic mixture, and chlorination at the primary position. So all three of these will be significant products. Now, with the halogenation with bromine, we're not going to get the primary product. We will get the secondary product, but in the same way, we're going to get a racemic mixture here, or in this case, tertiary product. So here, this is the tertiary site. This is where the bromination is going to happen, because the bromination happens so much quickly at the tertiary position. And but we will get a racemic mixture. And so even though the hydrogen was here, so if we draw the little dashes, the hydrogen was here, yes. But remember, the first step is the hydrogen abstraction. So when it's removed, we end up with the radical, this tertiary radical right here after the first step. And then we get the coupling with the bromine, and this can again happen from either side equally likely. So we can go from the front here, we can have the coupling from the front like that, or we can have it from the back or from the front. Yes, what's back or front depends. This is kind of badly drawn, but either direction essentially. And so that's why we get a racemic. When it comes to halogenation where we have a double bond, we have to think about the stability of the radical as well, just like we did for the tertiary radicals, which are more stable. Remember, allyl radicals are even more stable. And so we can see here when it comes to the which hydrogen is going to be abstracted most easily, it's definitely going to be this one here, or equally we can say this one here. It's the same, right? So either of these would be abstracted most easily, and so that's where the halogenation will occur. However, remember there's also resonance, and so that's something to think about when you get a allyl radical. So if we abstract this hydrogen here, there can be resonance involved. So we do one electron here in the pi bond, one electron from the former pi bond into this new pi bond, and now this electron goes here onto this one. So we can get the bromination of ultimately here, or we can get it here, which in this case doesn't matter, right? They're both the same position, one away from the double bond. However, if you don't have this kind of symmetry, that can make a different product, right? So we have to be aware of the possible, like we had for the carbocation rearrangements when we had ionic mechanisms, we have to be careful for the allylic radical and the resonance that it can undergo, and that can affect what the product will be. If we want to avoid the competing alkene reaction here, we can use N-bromosuccinicide here. And so, because remember, we can add bromine, right? We can have bromination. The other situation, you may remember from chapter 8 with addition reactions, we would get an anti-addition of bromine if we didn't have the light. So no HV, just Br2. We'd get the anti-addition where we get bromine here. It would go through a bromonium intermediate, have bromine on the other side. That was chapter 8, addition of bromine, the halogenation. These are going to be competing reactions. We'll have the radical halogenation, and we'll have the addition, the halogenation, the addition of Br2. So practically speaking, when we're trying to do halogenation, we often don't use Br2, although it could be used. Instead, we use N-bromosuccininamide, which is abbreviated NBS, and this provides to us one bromine radical, which we can then be involved in the radical addition instead of having Br2, which would ultimately give us the addition of bromine. So using NBS keeps the concentration of HBr and bromine low, so we don't have to worry about competing hydrohalogenations or halogenation addition reactions occurring. So in the propagation step here, when we use NBS, we get a bromide ion. So this does change the mechanism a little bit. The halogen gets involved in the hydrogen abstraction, so just the same as usual, right? But then the HBr here that is produced reacts with NBS, and that will form the Br2. So this keeps the Br2 concentration low, so we don't get as much addition, but that is a competing reaction. We are going to get some addition of bromine. And so then finally we get the halogenated bromine at the allyl position. Now, what I was mentioning before is that, given that we go through a radical intermediate, we do have to think about resonance and the fact that the radical can essentially move itself around. And so here we have an asymmetric molecule, not like the last one, which was symmetrical. So let's say the first thing that happens is we get the hydrogen abstraction right here. We produce the tertiary radical. Well, there's also another stable radical. So we have, I'll just draw the bromine atom for the NBS here. So bromine, got the bromine atom, got the hydrogen here. And so the first step is a hydrogen abstraction. Get a bond with the hydrogen here. And then that leaves the radical right there, right? And so we end up with this. Well, this right here. And then we can have the resonance here with this. So remember the resonance arrows here. Got this, this one, we'll put an arrow here, and then the last electron is right here. And so we have this radical right here, and that means that the bromine can, or the Br2 can come along in the next step, and we can have end up with the halogen abstraction. So we get this, making the bond, and then left behind. Whoops, a single head arrow here, not double head. Fish hook. There we go, and that's what produces for us this product right here. And so that's important to keep in mind when you're producing an allyl radical. The allyl radical is super stable. We can get this rearrange. It's like a rearrangement. It's actually just a resonance here, moving of the radical. Now, when it comes to radical reactions are extremely important to atmospheric chemistry. If you are interested in becoming an atmospheric chemist or climate scientist, you really, really need to understand radical reactions. The reason why radical reactions are so present is because radical reactions are often initiated by UV light, and up in the sky, these molecules are regularly exposed to UV light during the day. And then at night, there's no UV light. So there's kind of like a day-night cycle to these reactions as well. So one of the most important molecules in the atmosphere is ozone. So when ozone interacts with UV light from the sun, that UV light breaks it into oxygen molecule and an oxygen atom. And so that absorbs a UV light. And then later that oxygen atom reacts with oxygen very readily or actually to make a small amount of ozone at equilibrium. And so there's always a very tiny amount of ozone in the atmosphere. And fortunately that's true because that absorbs a lot of the UV radiation so that it doesn't reach the surface and burn our skin. So what comes in here is UV light, and what comes out is heat. And so that energy is kind of spread out. So instead of having this very intense photo energy that can break our bonds by hitting us with this UV light, it's dispersed here as heat in the atmosphere. And this process is spontaneous because we have entropy increased here, going from one molecule to two. Now, one thing that was very important back when I was younger was the ozone depletion, or the hole in the ozone layer. They often talked about it. It's not so much anymore because there were some important laws that were passed against the use of so-called fluorocarbons here, which would then react with ozone and turn it into oxygen. And so these became outlawed for the most part, and there were alternatives that were just as good that were come up with. And these were refrigerants generally, in refrigerators, air conditioners, also in hairspray cans. There were propellants, hairspray and stuff. But we stopped using these, and and that's just an example of how good laws can protect the environment. Unfortunately, climate change is not related to carbon dioxide, is not the same type of problem because the amounts of ozone and chlorofluorocarbons in the atmosphere are very, very tiny. For carbon dioxide, we're talking about billions and billions of tons annually released into the atmosphere, and removing billions of tons of anything is very, very difficult. So what happened here with the chlorofluorocarbons is these had a bond between carbon and chlorine. It was pretty easy to break. The UV light would hit it, and it would break the bond between the carbon and the chlorine, let's say, and produce a radical. Then those chlorine atoms would then react with the ozone, and they would get rid of it, right? They would eliminate it, and or destroy it. And so then there wasn't ozone in the atmosphere. This consumes ozone to protect us from UV radiation. And so these chlorofluorocarbons were not good for the ozone in the atmosphere. Now we have replacements to chlorofluorocarbons. These are called hydrofluoroalkanes. And these tend to just have a bunch of fluorine atoms in them. And the carbon-fluorine bond is much, much stronger than the carbon-chlorine bond due to the fact that it's very short and fluorine is very electronegative, so it's almost ionic. The Fluorine really, really pulls on the electron, so you've got a big partial negative charge here and a big partial positive charge, and they're almost a full partial negative and partial positive. So that makes this bond quite strong. And so because these carbon-fluorine bonds are so much stronger than the carbon-chlorine bonds, these work fine and they don't mess with the ozone in the atmosphere. They don't produce the chlorine radicals. They are greenhouse gases. They do absorb UV light and turn it into heat, but at least they're not depleting the ozone layer. And the bigger culprit with the greenhouse gases is the CO2 anyway. So one other thing that can occur with organic compounds is that they can react with oxygen and perform and create hydroperoxides. This is a very slow process, but it can occur. This especially can occur when you have a particularly stable radical intermediate. So for example here, this would go through a stable tertiary benzylic radical, super stable. So that really helps to create a radical which can then end up as this peroxide bond here. Remember, oxygen behaves as a diradical, so if we end up somehow creating a radical here and the oxygen is the diradical, so if we treat it like a diradical, then we can have a coupling that can occur right here, and this will still leave us a radical on the oxygen, which can then do a hydrogen abstraction and then produce this hydroperoxide. Hydroperoxide is also very common in the atmosphere as well. So in terms of the formation of this hydroperoxide, to give it a bit more detail here, we first start with some initiator like a chlorine atom or something, or a bromine atom, to do a hydrogen abstraction, and we get the radical. And again, if it's a very stable radical, hydrocarbon radical, that really helps. And then we have the coupling here between the oxygen diradical and the hydrocarbon. We still got a radical here. That radical can down do a hydrogen abstraction from a neighboring hydrocarbon, and then we finally get the hydroperoxide. And then the termination here would be just all these radicals here just coupling. And there are other potential coupling reactions that could occur too, right? We have this radical which could couple with it. But this is the main coupling reaction. So notice that this is a bit different too than most initiation reactions. Usually the initiation reaction involves a like if it's with a halogen, it involves a homolytic bond cleavage, but this one does not. So the propagation steps here can give, again, we can always add up all the propagation steps to get the net chemical reactions. So the coupling step here with the diradical oxygen and the hydrocarbon radical produce this peroxide radical here. Then finally the peroxide radical does a hydrogen abstraction. If we add these together, the first step produces the peroxide radical, the hydroperoxide. Then this is consumed in the next step to produce the ultimate hydroperoxide. Likewise, this produces the hydrocarbon radical, which is then consumed in the subsequent coupling step. And overall, we get that the hydrocarbon molecule reacts with oxygen and produces the hydroperoxide. And as usual, again, we get the overall reaction by adding the propagation steps in the reaction. Ethers are particularly susceptible to this, so we have to replace if you use like diethyl ether, for example, you've used these in the lab before, we have to replace these very regularly. They have to be consumed, otherwise they produce these hydroperoxide radicals, and these are very reactive, and they can be explosive if enough of them concentrates in the ether. And so when you're storing chemicals for long periods of time, you have to be aware of these types of reactions, because they could produce a dangerous situation. So you'll notice that the ethers that we get, they're not even held in bottles. They're held in a metal container, right? You remember that? And I would pour it out into the beaker. And so this is just to make sure they're not exposed to light, because that initiates this process. Now, I've mentioned before, earlier in the last lecture, I mentioned that in health and nutrition, often talked about are antioxidants that people eat. These antioxidants are important to prevent this kind of oxidation that can occur in molecules. So we all are doing metabolism. This involves oxidation of our carbohydrates, reaction with oxygen, right? Of carbohydrates, proteins, fats. And when we leave fats on the shelf, especially unsaturated fats like oils, peanut butter, cooking oil, olive oil, these ones are unsaturated fats. They have double bonds in them. And these double bonds here can potentially produce allylic radicals if they come into contact with a radical mechanism initiator. And so these can produce hydroperoxides as well, and when they do, these oils become rancid. So that's why when you buy your olive oil, you don't want to keep it for a year. When you buy your peanut butter, it can last, but you'll notice that it starts to get this off taste, and it's because it's got these hydroperoxides in it, and those are not things you want to eat either, because when you metabolize them, they produce more radicals. And so old cooking oils and peanut butter, eventually, past a year, you definitely want to throw these away. You'll often see that foods like this with unsaturated oils, they have something called BHT or BHA added into them. This is very common additive, food preservative additive for oily things. And so you can look at your peanut butter jar, and unless it's one of those natural peanut butters that don't last as long, it'll probably have this BHT in it. And the BHT is an antioxidant. It's a molecule that will be oxidized, will make a radical more easily than your unsaturated fats. It's because, I mean, look at this. Imagine you create a radical here, right? You've got all this, all these benzene rings here with these potential tertiary positions as well. You've got this huge potential for resonance to stabilize that radical and ultimately have it be quenched and not be a radical anymore. So these preservatives are radical inhibitors that are used in foods that have unsaturated fats, oils. So one molecule of BHT can prevent thousands of these. You don't need much. So here, what would more likely be the case is instead of breaking a bond here, you would have the removal of one of these electrons on the oxygen, and then you've got an allyl. You've got an allyl radical here, right? And these are highly stabilized by resonance, and ultimately they will react and get rid of and not be a radical themselves once they go and couple with something else. So BHT can undergo hydrogen abstraction to scavenge a radical that would otherwise indicate an autooxidation. So it can go, if there's another radical around, it can grab the hydrogen and turn that into a non-radical molecule, which won't go out and react with your body's molecules and mess them up. These are called antioxidants. There are lots of natural antioxidants as well. Vitamin E is one of them. And so you can see here a similar thing where if we take the electron off the oxygen, if we have the radical electron right here, lots and lots of resonance stabilization, right, all the way around this benzene ring and so forth. So vitamin E is a natural antioxidant in your oils, in your body, so in your cell membranes and fat cells and stuff. Vitamin C is, that's because it doesn't dissolve very well in water. Look at this huge nonpolar region. Right, it's so nonpolar over here. It's got a little bit of polarity here, but not much. Vitamin C is much more polar. Look at all this hydrogen bonding that it can do. And so it is the polar antioxidant that exists, in your water contents, such as your blood and the interiors of your cells. So back in chapter 9, we learned about the radical addition of the radical hydrohalogenation, which we had two ways. We can do hydrohalogenation without any peroxide, and this would give us the Markovnikov product, where the halogen atom would add at the more substituted carbon. And we also had the hydrohalogenation with the peroxide, and we were going to use the peroxide if we want the anti-Markovnikov addition with the halogen atom on the less substituted carbon. Now we can begin to explain why this would occur, right? And I think you might be able to expect why. It has to do with the fact that the tertiary radicals are the most stable, and so we're going to end up with an intermediate that's a tertiary radical. And ultimately, the halogen is going to add at the less substituted position. So let's finally get the payoff on this mechanism. So before, you didn't have to know this mechanism, but now this is an extremely important mechanism that you do need to know for the exams. So first of all, we add the peroxide, and remember, peroxide, these oxygen-oxygen bonds are very weak, or relatively weak, because these oxygens are both extremely electronegative. They both want their electron that's being shared, so they kind of rip their own bond apart with a homolytic bond cleavage here. See, pretty weak. It doesn't take that much energy to break this, about 150 kilojoules per mole. Then we have the hydrogen abstraction, and that produces for us a bromine radical, and this is the key to this reaction here. We end up with this bromine radical. So when the bromine radical now goes and reacts with the and does the halogen addition here, what happens is we have a addition here where the pi bond, so this is a radical addition, where we have the electron from the pi bond goes into making the bond to the bromine, and this electron here, the radical, the unpaired electron, the bromine, goes into that bond, and we get a bond here, and then this electron is going to go on the more substituted carbon. Okay, the tertiary radical will be favored here. The other is a possibility where the bromine adds over here instead, but much less likely. The tertiary radical is much more stable. And so at that point now, the last step for the addition is just going to be a hydrogen abstraction to finally make this into a bond. But you can already see that the bromine is attached at the less substituted position. So finally, that's the propagation step. Just as I drew there, we get the addition of the bromine atom, produce the tertiary radical intermediate, and then we have a hydrogen abstraction from the HBr. Remember that HBr was produced, let's see, we use HBr here. HBr can be produced by hydrogen abstraction somewhere else, and we get now the final product here, where the bromine is attached in less substituted position. So the carbon radical then extracts the hydrogen and produces the final product. The termination step is just all these bromine atoms that were produced coupling, and bromine radicals are destroyed. Any two radicals can do this, not just bromine. Bromine will be the one most significant here. In terms of the energetics of this reaction, so the anti-Markovnikov addition is generally spontaneous, so it's going to have a negative delta G. The radical addition of HCl and HR are non-spontaneous, so these are going to have a positive delta G. So if we want to do this radical addition, we want to do this with bromine. Okay, and again, we could calculate this, right? If we calculate the delta H based on the bonds breaking and the bonds making, and then calculate the entropy, we could determine this. This generally is true. So let's think about the enthalpy and the entropy. So for the addition of HCl, it's going to be exothermic, also for HBr in this last step here. So this is the propagation step here, and we're going to get a negative exothermic for HBr as well. It's going to be endothermic for HI. And let's think about why. Just very simply, without doing all the numbers. It's because the carbon-chlorine bond is stronger than the carbon-bromine bond, which is stronger than the carbon-iodine bond. Okay? So the carbon-iodine bond is weaker, so we're getting less energy out when that bond is formed compared to the energy we had to put in to break the pi bond. And so that's why these two are exothermic, whereas for making this carbon-iodine bond is endothermic. In terms of entropy, these are all, in terms of the entropy, these are all going to be decreasing in entropy because we're going from 2 substances to 1, okay? So these are all going to be decreasing in entropy, which means the entropy is negative, which means this whole term together is going to be positive. And so it's all now about the competition between how exothermic and the exothermicity and the entropy. So the iodide radical here is also much more stable. So here in the second propagation steps, now this is where we grab the hydrogen from the halogen here. The entropy term is going to be close to 0. We're starting with 2 reactants. We're getting 2 products. But the enthalpy term here is going to be positive for the HCl because the HCl bond is harder to break. It's a stronger bond. And so that step is going to be endothermic. Whereas the hydrogen-bromine and hydrogen-iodine bonds are weaker bonds because they're longer. And so the result is that these terms are going to be exothermic. And this reaction is going to be exothermic for HBr and HI. Notice the only one that's exothermic in both cases. The first propagation step is exothermic for the bromine. It's exothermic for the second propagation step, exothermic for the bromine. Whereas for the iodine, it was endothermic. It was endothermic here. And now for the chlorine, it's endothermic on the second step. So for the HBr, it's exothermic in both steps. It's the only one. And so the result is that you're going to want to do this with bromine. When you do the addition reaction to produce alkyl halide, you're going to want to use HBr. You're not going to use HCl or HI. And this is going through a radical mechanism. So again, if it's not chiral, then you're going to get a racemic mixture. If it's chiral, if you end up with a chiral carbon, rather, you're going to get a racemic mixture. You're not going to get one in an atom or the other. You're going to get both. Also, in terms of the potential for other reactions, remember that we have potential for adding bromine in other places. For example, in the allyl position. The take-home message here, sorry to confuse the point, is that you're going to get a racemic mixture when the halogen adds, and the halogen should be bromine. In terms of, let's see where I'm at here. Yeah. So I think I'm going to end this lecture at this point. It's been about 45 minutes. For the last part of the lecture, we're going to talk about polymerization reactions. These are the reactions that are important to produce all of the plastics and the PVC pipes that are used in our house. So that will be the last set. We'll talk about polymerization, and then finally we'll talk about synthesis in the last lecture, which will be pretty short. I'll see you in that one.